Hello everyone, my name is Harshvardhan Purohit and today I'll be teaching you about lens maker's formula. This formula has a lot of practical applications. It is used by lens makers, it is used by watchmakers, it is used by glass makers to make lenses of a particular or a given focal length. What is the use of finding the focal length? It helps us understand where the rays of light meet or converge or diverge from after passing through it. So let's just deep dive into finding out what is a lens. So a lens is a transparent object that is usually made of glass or plastic, and glass also has many various types like flint glass or ground glass. And this lens refracts or bends a ray of light when the ray of light passes through it. So lenses are mainly classified into two types, convex lens and concave lens, as you can see on my screen. So how do we differentiate between the convex lens and a concave lens? Let's say I don't give you this description and I ask you which is a concave, convex. Some people might struggle with it, finding out and being confused with finding out which is a concave or a convex. So to simplify it, convex lens is thicker at the center and thinner at the edges, while a concave lens is thinner at the center and thicker at the edges. How do I better remember it? So better way to remember this is consider a arc. Doesn't this, and a person, let's say you, doesn't this look like you are entering into a cave? Similarly, as you can see, when these two arcs come together, this is what is a concave. So this method is personally used by me, and if it suits you, you can also use it. So with this, lenses has a lot of everyday applications also, and that is why even the formula comes into picture. Lenses are used from eyeglasses, that is spectacles, to cameras, to watches, and many more. So now let's just get into deriving the formula. So what is the formula? The formula is given by 1 by f is equal to n2 by n1 minus 1 multiplied by 1 by r2 minus 1 by r1. You might ask, what are these terms given on the screen right now? So f is the focal length of the lens. Here I have considered a convex lens, and it can also be done for a concave lens. So here focal length, f is the focal length of the lens, n2 is the refractive index of the material of the lens, n1 is the refractive index of the outer media, r2 is the radius of curvature, that is the distance between optical center to the center of curvature of the face of the lens. For example, let's consider this first face. This first face has, if I extend it into a circle, we find the radius, the center of curvature of that sphere, and the distance between that center to the optical center is given by is known as the radius of curvature. So I'll be using the terms face 1 and face 2, and the radius of curvature of the face 1, that is this face, is given by r2, and the radius of curvature of the second face is given by r1. Now let's understand how we get this formula. So let's consider the first face. The first face, as I already mentioned, is the radius of curvature is given r2. And then let's consider a point source u over here, which is u distance away, or the object distance. This point source emits a ray of light which strikes this spherical surface, and since there's a change in media, n1 is rarer, n2 is denser. Since there's a change in media, this ray of light at this point refracts, and since it's going from a rarer medium to a denser medium, the ray of light bends towards the normal, and let's say after refraction it's at this point. Let's consider this the distance to be v dash, that is the image distance, and we know the formula for refraction through a spherical surface when the ray of light is going from rarer medium to a denser medium is given by n2 minus n1 divided by the radius of curvature r2 is equal to n2 by v dash, that is the image distance, minus n1 by u, that is the object distance. Now, since we consider the first phase, let's consider the second phase. Considering the second phase, as I already showed you that there is already a refracted ray. Considering the ray from there, this ray again due to the change in medium, it's going to refract, and since this time it's going to be from denser medium to a rarer medium, it's going to refract away from the normal, and let's say it hits this point here closer to the lens. So for this face of the lens, this point acts as the object, because now because even after we trace the ray back, it's going to come at the same point as the object or the point source that we already have considered. So hence this now acts as a object for the second phase of the lens, and hence v dash becomes the object distance, and v or the final image distance, and r1, as I already mentioned, is the radius of curvature of the second phase. And the formula, as we know, is n1 minus n2 divided by r1, radius of curvature, is equal to n1 by final image distance v minus n2 by object distance or virtual object distance v dash. Now let's just merge the two lenses that we just saw. What's going to happen? We're going to get something like this. It's very clumsy, I know. So let's just simplify it a bit. So this is the final process of refraction happening. Let me just repeat it to all of you. This is the point source. Ray hits the first phase, refracts. Then it hits the second phase, refracts again. And hence we get the final image at this point where the distance is v, object distance is u, radius of curvature of second phase is r1, radius of curvature of first phase is r2. So now let's just look at the derivation. As we already have this formula given, as I already showed you previously, and then that is the refraction formula at the first phase. This is the refraction formula at the second phase. Let's add these two formulas. We get this LHS n2 by v dash minus n1 by u plus n1 by v minus n2 by v dash is equal to n2 minus n1 divided by r2 plus n1 minus n2 divided by r1. As you can see, here we have n2 by v dash minus n2 by v dash. These two can just get cancelled out. So let's cancel them. What we remain is with n1 by v minus n1 by u. And from here, let's take n2 minus n1 common outside. So let me just show you. When I take this out common, what I remain is with is this, because since there's a inversion in sign, I'm gonna get a negative sign at top on r1. So hence we get minus 1 by r2 minus 1 by r1. Here, as you can see, we have n1 common. There's so many. There's n1 here. Let's take that into the denominator or on the RHS. And since we know the object distance varies from distance of least distinct vision to infinity, there can be any distances. So hence let's consider object distance to be at infinity. And let's say we want the ray of light to focus at a given point. Let's say, for example, we are wearing spectacles. Then we want the rays of light to focus on a retina. So hence the image distance should be equal to the focal length. So hence when we substitute 1 by infinity, that is n1 by infinity is given as, of course it gets cancelled out, which becomes 0, and n1 by v. So hence since v is equal to f, it becomes 1 by f, and since n1 we have taken it to the denominator, it becomes n2 minus n1 divided by n1 multiplied by 1 by r2 minus 1 by r1. And that, friends, is the formula for lens makers. Thank you, and now I am open for any queries that you wish to ask. And
can we use let's make a formula for plane?
for?
For plane mirror?
Yeah, you can. You can, but then you can use, but then one of the radius of curvature is going to be not considered.
How? Can you explain?
Like, see, focal length will, in the end, we're going to get it as infinity because, see, N2 and N1, right? This is, lens maker's formula is basically used for lenses, not mirrors. My
It
bad.
does not have a curved surface. Yeah, so it can never be used for a plane mirror.
Yeah, it's basically meant for lenses rather than mirrors. Even you can not even use it for concave mirrors or convex mirrors.
So, suppose I'm telling that because plane mirror, it first of all it does not refract.
It refracts. Like.
So does this apply for any other surface which has a radius of curvature? Will this be applicable?
If it's a lens or if where there's refraction happening, yes.
So imagine you have a red monochromatic light or a violet monochromatic light. You pass it through a convex lens. Which one do you think will converge first, the red one or the violet one?
The violet one has a lesser wavelength, as we know. So hence that's because of it deviates easily. So hence that's going to converge more closer towards the closer to the optical center.
You said that this is transformed. Does it work for both convex and concave lenses?
Yeah.
Then how about the focal length? You can say if we change the lens.
So for convex lens, the focal length we're going to get it as positive, and for the concave lens we're going to get the focal length in negative because there's going to be a change in sign of R2 and R1. Any other queries?
Is lens maker formula always applicable? What if I were to change the medium when it was the mirror, the lens?
Okay.
For example, if it was slightly pale, or if
Yeah, that's why there's two refractive indexes considered here, N2 and N1. So if there's a change in outer medium, then there's going to be change in refractive index. For example, as previously asked by one of the evaluators, if the lens is immersed into water or any other liquid, so N1 changes accordingly. Jenny?
So we know that this is not always valid.
Yeah.
So when will it not be valid?
For example, if there's a change in temperature, for example, when there's when the lens, which is supposedly considered to be thin lenses, and whenever if it's thick lenses, then it's gonna not be considered.
So any other one more?
One more. Then there's a chromatic aberration. Oh yeah. Any other?
Okay.
Thank you.